This third video deals with impulse or the change in momentum. So this is the part where we kind of step away from conservation momentum. Conservation momentum dealt with enclosed system. And every example we had an enclosed system. We said these two things are hitting and nothing else is a concern, right? So what happens if the system's not enclosed? What happens to, if there is an outside force that's going to exert itself on something? So what happens when the enclosed system is gone? What happens next after the collision? And for that, we have to look at what causes the momentum of an object to change. Well, this isn't much different than Newton's laws. Again, Newton tells us that if we want to cause a change in velocity, there has to be an outside force. Well, if we want to have a change in momentum, there has to be an outside force. Forces cause acceleration. Acceleration means the velocity is going to change. And if the velocity changes, well, then the momentum changes too, because momentum, not impulse, but momentum is mass times velocity. So if there's an acceleration, then by definition, this changes, which means the momentum changes, right? So a force is what causes an acceleration. Forces cause acceleration. So now, first of all, let's kind of go back to this. Impulse, what's the symbol? Well, momentum is a P, and the change in momentum, well, the change in something is delta. So impulse's symbol is delta P. We could also say, just by its definition, the impulse equals the final momentum minus the initial momentum, right? And in everything we talked about before in these enclosed systems, there was no change. But now, if we looked at different objects, well, different objects went through a change. So let's go back and just look at one. These two balls of clay, when they hit, well, if we look at the system, the total momentum was absolutely conserved. The initial momentum of these two added up equals the final momentum of these two, right? But if we looked at just the green clay, well, that object definitely changed its momentum because its direction changed and its velocity changed. So things happened to that. So if we just looked at the green one, and if we just said, "Oh, it's moving along, something hit it," and this was its momentum in the beginning, and then this was the momentum finally, there would be a difference, right? So we kind of can define these systems, right? And if we look at the two football players, same thing. The total momentum of the system, we could deal with conservation momentum. But if we were just focused on this guy on the left, well, his momentum changed. Why did his momentum change? Because there was a force applied to him, right? And there was a force from the other guy. As a matter of fact, there was a force from both of these people applied to them. So, impulse is that, right? It has to do with what causes something's momentum to change. Now, it's not just a force, but force has to have something to do. If I want something to change, if I want the momentum to change, I have to apply a force, right? Because forces, again, cause acceleration, and acceleration causes velocity to change. But there's more to it than that. Can I just apply a force? No, I have to think about that a little bit. It's not just what force did I apply, but it's also how long did I apply that force. So the change in momentum equals the force times the time, right? How much force did I apply, and how long did I apply that force? If I applied it for a long time, well, then it's going to keep accelerating, velocity is going to keep changing. If I applied the same force for a short time, should be the same amount of acceleration, but just for a short amount of time, so there'll be a shorter change. So the time matters. All right, so let's say we got a shopping cart, and this shopping cart has a mass of 12 kilograms, and the initial velocity is 0, and then someone comes along and they push it. And they apply a force. They don't keep pushing it, but they apply a force to the right of 20 newtons, and they give it a push for like 2 seconds, right? So they grab it, they give it a push. And I ask the question, what is the final momentum? Well, the initial momentum was 0. So initially, my momentum is mass times velocity at 0. My final momentum, I don't know, but I do know that impulse equals the final momentum minus the initial momentum, where in this case the initial momentum is 0. And then the impulse is force times time, so 20 newtons times a time of 2 seconds. And before I do this, let's go ahead and take a look at these units for a second, because this would give me a Newton second, which is a little weird. But what is a Newton? Well, a Newton is kilogram meter per second squared. I have seconds on top, and it gets rid of 1 on the bottom. Now my units are going to be kilogram meter per second. So the units work out right for momentum, and I'm going to be 40 kilogram meter per second. So if this man applies a force of 20 newtons for 2 seconds, the change in momentum will be 40 kilogram meter per second, which in this case, because the initial velocity was 0, that'll be the final. And if I wanted to get the speed, well, then I could divide it by 12. So 40 divided by 12. 40 divided by 12. How fast will it be going? Well, the velocity will be 3.33 meters per second to the right. So there is one example of changing something's momentum because we're applying a force to it. Let's do one more quick one, and then you have plenty to look at so that you can start doing the problems. Let's say I have a wall. You know what? I'm going to get rid of that because that was an ugly wall. Let's do this slightly different. There we go. I have a wall, and I have a tennis ball. There we go. Doing this with the pen isn't the best idea, but that's all right. And this ball has a mass of 1.3 kilograms, so it's a pretty heavy ball. And it is coming in, so it strikes at an angle of 20 degrees. Now, when it bounces off, just like most things that bounce off, it is going to bounce off and not change the angle, and we'll explain why we don't expect to see the angle change in a second. And it is now going the other way. Now, it's a hard ball. It is a hard wall, so I don't expect there to be a change in shape or anything like that. There's not a lot of sound, heat. So this is, in a lot of ways, this is somewhat of an elastic collision. Now, we can't deal with it as an elastic collision because I don't know what the wall is going to do. But we're going to say that it bounces off going the same speed. So if it comes in going 10 meters per second, after it hits the wall, it doesn't lose much. So we're going to say it leaves at 10 meters per second. So let's say this was the case. I have this ball, and I simply bounce it off the wall. And it comes in at a certain speed, and it goes out at the same speed. All kind of realistic things, right? If I threw a rubber ball against the wall, it's going to bounce off going the same speed. It doesn't lose much. And let's say if the time, which means the time that the ball is in contact with the wall, which is a really small amount of time. Let's call it 0.05 seconds. So 5/100ths of a second, right? Which is a short amount of time. But then if you think about it, if you bounce something, it's not in contact with that other surface for very long. What is the force? All right. So this second problem, I'm going to back up a little bit. I have this ball. This ball is coming in, and it is going to strike the wall, and it's going to bounce off the wall. Now, much like things that bounce off, the angles don't change that much, right? If you do a bounce pass with a basketball to somebody, the angle that comes in hitting the ground is the same angle that comes out. It doesn't bounce in some weird way, right? These angles tend to be the same, and there's a reason for that, and we'll see that in a second. So the angle coming in is 20 degrees, and the angle going out is 20 degrees. Also, If it's a hard ball that doesn't lose shape, it's designed to bounce like a basketball or a rubber ball or something like that, well, then it's not going to really lose much speed on the bounce. So if it's coming in at 10 meters per second, it's going to go out at 10 meters per second, right? It's a hard floor, it's a hard ball. So if I assume these things, then this is what I have. And I want to know what's the force. What's the force that the wall exerts on the ball? Or what's the force that the ball exerts on the wall? It doesn't matter because Newton's third law tells us you apply force, an object applies an equal force back. So what's the force? And I guess we'll just say what's the force of the wall, but it doesn't, like I say, doesn't make a difference. All right, so this isn't a conservation momentum problem because momentum is not conserved in this case. It definitely changes, and we can't deal with conservation momentum because it's not an enclosed system, right? This wall is attached to a building, right? So it keeps on going and going. So we can't really use that. So this is definitely an impulse problem. The other reason we know it's an impulse problem is because I'm looking for a force. And impulse, or the change in momentum, equals force times time. So I've given you a time also, so we're on our way here. So let's look at this. Now this is more of a two-dimensional problem. And I'm going to use this same thing, but then understand, first thing we have is we have our initial information. And initially, I have a 1.3 kilogram ball going at 10 meters per second, so I have a total momentum of 13 kilogram meter per second. And I'm still going to break it up, though. I'm going to break it up into its horizontal and vertical component. So initially, I have 13 times the cosine of 20. How much momentum is there to the right or horizontally? So it's going to be 12.21 kilogram meter per second. And then I have 13 sine of 20, and this one's going to be 4.45 kilogram meter per second. And it's going to the right, so this is positive, but it's going down, so this is a negative. So this is my initial information. Now, what else do we have? Well, after the collision with the wall, it still has a momentum of 13 kilogram meter per second because it's still going 10 meters per second. It still has the same mass. So I can do the same types of things, but it's the same number times the sine of 20 degrees. So it's still going down, and it's still going down with the same momentum. So if I look at this, my final here stays the same. And if I do 13 cosine 20, I get the same number, but now it's moving to the left. So if we look at this then, my change in momentum only occurs in the horizontal direction. My change in momentum vertically is 0. It was going down and it's still going down. So it has the same downward momentum both times. So my vertical change in momentum is 0, which means there is no vertical force. There is none. Horizontally, though, I have my final. So just looking at the horizontal components, I have my final, which is negative 12.21 kilogram meter per second, minus my initial, so minus 12.21 kilogram meter per second. So my change in momentum total is 24.42 kilogram meter per second, and it's just to the left. Which makes sense, but it makes sense because the change in momentum, come on, there we go. Change in momentum equals force times time. So if the impulse is to the left, well, then the forces must be to the left. And first let's keep talking about that. So the force that acts on the ball must be a force to the left. Well, if this is the wall, and we know about forces, and we do know about forces, what is the force that acts on the ball? Well, it's the normal force, right? And what direction can the normal force push? Well, in this situation, the normal force can only push to the left, which is why I know these two angles had to be the same, right? So the normal force is to the left, and when I look at this stuff, it has to be to the left. So I have 24.42 kilogram meter per second equals the force that I don't know times 0.05 seconds. I divide by 0.5 seconds, 0.05 seconds. I'm going to have kilogram meter per second squared, which is just what the force is. And it's going to be kind of a big force because we have this heavy ball moving fast. 24.42 divided by 0.05. The force is going to be 488.4 newtons to the left. And again, we even know the name of this force. This would be the normal force, the force that stops an object from falling through a surface. So there are two quick problems with impulse or showing how we could change momentum.